Good afternoon, Internet. I am Matt Booyak, and in this video we'll be taking a look at the 57th problem from the Project Euler Problem Archive. Now, this problem asks a question about the infinite continued fraction representation of the square root of 2. This claims that 1 plus 1 over 2 plus 1 over 2 plus 1 over 2 plus ... on to forever is equal to the square root of 2. And if you haven't seen this before, you're probably wondering how we know that this is even well defined, or if it is at all. And the way we usually think about such things is to consider the sequence of partial evaluations of this expression, which we can see over here on the left. But even given this list, you might wonder what it means to partially evaluate something that has its innermost evaluation infinitely deep. Well, if we look at this right-hand side, we'll see that if we add 1 and take the reciprocal and then add 1 again, we get back the same thing that we started with. And so we're going to apply that same process starting with the number 1. So over here, if we start with 1 and add 1, we get 2. Take the reciprocal, we get 1/2, and then add 1, we get 3/2. And that is our first approximation of the square root of 2 based on partially evaluating this expression. It's not a very good approximation, but as you can see, calculating more and more partial evaluations of this expression seems to be getting closer and closer to the square root of 2. And if we could show that these partial evaluations get arbitrarily close to the square root of 2 as we calculate more and more of them, perhaps we're justified in using this equal sign here between the square root of 2 and this expression on the right. In any case, that's a very deep and interesting subject in its own right, but it's not the question we're asked to deal with today. The question we're asked is that if we can consider this sequence of partial evaluations represented as fractions, we'll notice that most of the time the top of the fraction, the numerator, has the same number of digits as the denominator, the bottom of the fraction. But sometimes, and the first time it happens is in the 8th element of the sequence, the numerator will have one more digit than the denominator. It gives this example here, 1,393 over 985. And we're asked to count the number of times that happens in the first 1,000 elements of this sequence. Now, you may notice that these values are roughly doubling each time this process is repeated. And so they're expected to grow exponentially. That means that, as with the last few videos, we'll need to use our big integer class in order to deal with this effectively. Fortunately, just a few videos ago, I showed how we can add the ability to convert our big integers into strings, and so that's going to help us count the number of digits. We can just convert the big integer representation of either the numerator or denominator into a string and see how many digits it has. Now, before we can actually get to writing some code, there are a couple more things we're going to have to deal with. We need to figure out how to actually add 1 to a fraction. For some of you, that may be basic. For some of you, you may need to think back to middle school algebra or earlier. How do we take the reciprocal? And then also, how do we deal with the case where the numerator and the denominator have some common divisor? For example, if this first element here was 300 over 200 instead of 3 over 2, we would want to represent that as 3 over 2, dividing both the top and bottom by 100. So how do we deal with that? Well, let's get into it. As usual, we'll copy our template directory to make our problem directory, enter our problem directory, and open our analysis file. So I want to just go through the first few elements of this sequence so we can get a feel for how this works. Let's just label this column P over Q. This one is going to be 1 plus P over Q. And then this one is going to be 1 over 1 plus P over Q. And then we'll add 1 again to get the next row of this table. So we start off with 1 over 1. That's our starting point. Adding 1, well, we're going to make sure that the denominators match. So we want to write 1 as 1 over 1. And then adding those, that gives us 2 over 1. Taking the reciprocal is just going to be flipping the numerator and denominator, that is swapping them. And so that gives us 1/2. And then adding 1 again, we're going to write that as 2 over 2 plus 1 over 2 is going to give us 3 over 2. Just to do one more example, we would add 2 over 2 plus 3 over 2 is going to give us 5 over 2. Taking the reciprocal gives us 2/5. And then adding 1 again is going to be 5 over 5 plus 2 over 5, which gives us 7 over 5. And I think you probably get the idea. In particular, when we add 1, we're just going to add the denominator to the numerator. That's the effect that adding 1 will have. So now we need to work out how to deal with the case where the numerator and the denominator have a common divisor. But what we'll actually end up seeing is that that will never happen. And it's not too difficult to prove. We can first note that our first element here, 3 over 2, 3 and 2 do not have a common divisor. And basically we'll prove inductively that none of the other terms are going to have common divisors either. And we'll do that by contradiction. So let's say, suppose GCD of P and Q is 1, but P plus Q over Q, or excuse me, we want to say GCD of P plus Q and Q is greater than 1. And we'll say that D is that greatest common divisor. Okay, well that means that there must be some multiple of D. Call it, we'll say, let Q equals AD. So some multiple of D is equal to Q. And it must also be the case that some multiple of D is equal to P plus Q. So we'll say P plus Q is equal to BD. Okay. Well, now we can substitute this first line into this second line, and we get P plus AD equals BD. And subtracting AD from both sides, we get P is equal to BD minus AD, which is equal to B minus A times D. That is, we see that P is also divisible by D. So we'll say that is D divides P and D divides Q, a contradiction. That is because we started by assuming that there was no divisor greater than 1 that, that divides both P and Q. Okay, so this means that by using this process of taking the reciprocal and adding 1 and doing that multiple times, we will never create a fraction that is not in reduced form. There will always be no common divisor greater than 1 for both the numerator and the denominator. And with that out of the way, let's get to writing the code. So we'll go back over to our main.cpp, and we're going to need to include our BigInt. So we'll say include BigInt.h. We'll modify our makefile to include our number theory library. And let's just take a look at that big integer class real quick. And the main thing that we're going to need is this add here, which is going to let us add one big integer to another. And we'll also need this toString function, which allows us to convert a big integer to a string. Okay, so then we can say BigInt a. We're going to initialize that to 1. BigInt b, and we're going to initialize that to 1 also. Now, the reason that I've named these a and b and not something more useful like numerator and denominator or top and bottom, something like that, is that we want to be able to efficiently swap the top and bottom. And so we're going to do that by having pointers to our big integers, which are trivial to swap. It's just moving a few bytes around. So we'll say BigInt pointer denominator equals a, address of a, and BigInt pointer numerator equals address of b. All right. And then we're going to want to keep track of our solution, which is going to be the number of times we see a numerator with more digits than the denominator. So we'll start that off at 0. And we'll say for int I equals 0, I less than 1,000, increment I. Recall we're looking for the number of times the numerator has more digits than the denominator in the first 1,000 terms of our sequence. Okay, so let's start by calculating the first term. So we need to add 1 first. Remember, to add 1, take the reciprocal, and then add 1 again. And so to add 1, we're going to add the denominator to the numerator. So we'll say numerator add star denominator. Then we're going to want to swap the numerator and denominator. That is take the reciprocal. So we'll say swap. And we want to be clear that we are swapping the pointers. As I said, pointers are small, easy to move and copy, and so it's very efficient to swap 2 pointers. So we'll say BigInt pointer, and that's going to be a and b. Excuse me, numerator and denominator. Okay, and then we want to add 1 again, so we'll say numerator add star denominator. Okay, and now we want to check if the numerator has more digits than the denominator. So we'll say if numerator toString dot size is greater than denominator toString dot size plus plus solution. Okay. And then down at the bottom here, we'll say printf solution equals solution. Now, before we actually run the full version of this, I just want to run the first 10 terms and actually print them out. And so here we'll say printf. We'll just say a sub I is equal to %s over %s. And so that's going to be index I plus 1 and numerator to string dot cstr. We have to convert to a C style string, and then denominator to string dot cstr. Normally I would not have a line of code this lengthy, but it's just for demonstration purposes, and we'll be deleting it in just a moment, so I think it's probably fine. Let's go back to our shell and make and run, and we can compare this list here to our problem description over here. And we see that the first few terms are 3/2, 7/5, 17/12, 41/29. And over here we have 3/2, 7/5, 17/12, 41/29, and so on. And we can see the 8th term here is the example that they give of the numerator having more digits than the denominator. Okay, so now let's run the full thing. Get rid of our printf here and crank this back up to 1000. Okay, so it gives us an answer 153. So let's go back to the archive here. I haven't even bothered trying to sign in because it so frequently signs me out anyway. Okay, now we'll go to the second page and problem number 57, and we see that that does in fact match our answer. So as always, thank you for watching. In the next video, we'll tackle problem number 58.